So, if you go to the stock market and look at the price of say a favorite company's share, so what you would observe is the following. So, if the horizontal axis is the time axis and this is the price axis, tells you what is the price, then you will see starting from a certain time price you will see some zigzagging motions like this. So, up to you observe it up to time t and you observe this zigzagging motion. This is of course random, nobody knows what the next price is. So, if a particular scenario evolves, you have a particular path, it is called a sample path. So, if another scenario evolves, there would be another path. For example, it could be like this. The stock price is going down, 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 down and you are in a bad shape and then it again climbs up and again falls down, down, down and again then again climbs up. So, under a different scenario it has a different path. So, it is sample path 1, it is sample path 2. So, it is what type of scenario one evolves. Now, of course, you can ask me what is this term scenario that you are talking about, what is the meaning of this goddamn word scenario. We will come to this very soon, but how do I model such zigzagging paths, what way to model it? Is there any mathematical way to say that or can I construct a stochastic process whose sample paths are represented in this form? Let us to do that, we need to study what is called Brownian motion. Brownian motion is a type of stochastic process which will help us to model stock prices at the end. So, the whole term Brownian motion comes from the name of Robert Brown, who first studied the movement of pollen grains in water and he found that they were having very zigzag haphazard movements. But it is not so immediately apparent that you can just start writing about this particular stochastic process. We need to have some more idea and build upon some simpler stochastic process. So, this will begin, we will begin by introducing what is called symmetric random walks, where there are only two possibilities. You can either go up or down, that is like a coin toss, head or tail, and that here I can have infinite such possibilities, infinite such sample paths. Here of course, and there it could be infinite possibilities also. Here also we will have infinite possibilities, but generated out of only two possibilities. So, symmetric random walk. So, you take a fair coin and then you keep on repeatedly tossing it. So, it is a, so this is a stochastic process which I will write in short from now on as stochastic process generated by repeated tosses of a fair coin. Okay. And if you look at it very carefully, what I mean by this. So, you start tossing the coin. So, repeatedly you are tossing omega 1, omega 2. So, omega 1 is either head or tail, omega 2, omega 3, omega 4, 5 and so on and so forth. Suppose you have here head, head, tail, tail, head, 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 tail, tail, tail and it goes on. So, this is one particular scenario that has evolved. You could have another scenario, say omega bar, which is consisting of say omega 1 bar, omega 2 bar, omega 3 bar, omega 4 bar, omega 5 bar. It could be something like this. tail, tail, head, 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 tail, 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 head, 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 and so on. So, these two are different scenarios, and these two each would generate two different sample paths. So how do we generate this symmetric random walk? So, these are two different scenarios, two different scenarios. Now, construct a random variable xj. Xj, which takes the value 1 if j is equal, sorry, if omega j is equal to head, and takes the value -1 if omega j is equal to tail, if tail appears, and 1 if head appears. So, now you define a stochastic process. So, define a new stochastic process. Mk, k equal to 0 to infinity, or let us, we can need not bother, we can also fix it up to some time. It could be some time capital, say k is say 25 something, here 25 or 30 whatever, but in general it is alright to take plus infinity, just a sequence, where Mk is given as follows. Each of these Mk's are calculated by starting from m0 equal to 0, Mk is equal to j is the sum from j from 1 to k to xj. So, let us see what would happen if one particular scenario like this evolves. Let us see then what is the sample path of this. This symmetric random walk is also called a drunkard's walk. So, somebody has had a good drink and he has become drunk, and if you look at his walk, so if a drunkard would walk like this, if I am here, so I start from here, then I can just go like this, and he goes like this, just it is just, or like this, I am coming here and then I am going there, something like this. So, this sort of thing you will immediately observe as I start, say, checking out with this scenario. So, here is my k and here is my Mk value. Now, the first one here has turned out to be head. So, M0 is 0, let me write -1, -2, -3 and so on, -4 here, 1, 2, 3, 4 and so on. And of course, that here also you have to have k values, which is 1 or maybe not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on and so forth. So, M0 is 0, this is 0, is 0. Now, you toss a coin and you have head, omega 1 is head. So, you go up by +1 because xj will take +1, because M1 is just x1. So, here is the value of M1, this is your M1. So, you join M0 and M1 by line. So, 0 is M0. And then you again add head. So, M2 is again 1. I am looking at this scenario. M2 is, you go by 1. So, it is 1 plus 1 now 2. So, M2 is 2. So, you join again by this line. But M3 is tail. So, you will drop by 1. So, it will be -1. So, you will again drop back to the point 1. So, this is your M2 and this is M3. And then omega 4 is again tail. So, it drop back to 0, again you minus 1, subtract. So, this is your M4, it is 0. Again then you have head for omega 5 say. So, here you have omega 6, omega 7, omega 8, omega 9. So, for M4 your tail you have come to 0, again then it goes up again for M, it goes to plus 1 again. So, this is your M5, again it goes up to 2, M6, but then you have tail again. So, M7 comes down to plus 1, again you have tail. So, M8 comes down to 0 because you are adding up everything, at every step you are going up or down. So, you add up in this fashion and you move like this. So, M8 I have here, omega 8 is again, omega 9 is tail. So, again I have to go down. So, I go down by, so from 0 I will have to go down by 1. So, I will come to minus 1. So, this will be our M9. And if suppose M10 omega 10 is head, then it will again go up to 0 at the 10th place, because it will again add 1. So, it will become your M10. So, what you see that the symmetric random walk is providing me some zigzag looking curve, which might tempt you to think that possibly these two have some relationships. They do have some relationships, and we will talk about that slightly down the talk. But let me tell you some more properties of this symmetric random walk MK. So, here is my stochastic process, and this stochastic process is called the symmetric random walk. Of course, we are not mentioning, but underlying we are always taking some probability space and all of those things. So, now we will this particular random process or stochastic process has independent increments. What do I mean by the fact that they have independent increments? What I mean is the following. So, if you take certain numbers, sometime say some Km, then you have the following. You have Mk1, that is, once you consider non-overlapping intervals, then this difference is independent because they depend on independent coin tosses, because coin tosses are independent. The coin toss at the second level really doesn't, the second outcome doesn't really depend on the first outcome, right, when you do a repeated coin toss. Sorry, K2 minus K1, Mkm minus Mkm minus 1. So, these random variables are independent. All of these random variables, these form a set of independent random variables. So, that is, once this happens, this is when we say that it has independent increments, and this actually has independent increments. These are independent because their difference, which really does not depend on the coin tosses here, does not depend on the coin tosses here, and so you have independent increments. So, this change that you see here does not depend on the change that you see in this interval or the change that you see in this interval, right. So, you can still observe that it is like a drunkard walk. So, drunkard walks like this, goes down, goes up. In George Gamo's famous book 1, 2, 3 infinity, this has been described in a very, very nice way. How do you see here? My success probability this occurs with probability half and this also occurs with probability half. So, if you observe that exponential of xj, expectation of xj is 0 because it is 1 into half plus minus 1 into half. Variance of xj so, what is variance of xj? Exponential x minus xj whole square, which is 0. So, it is 1 into half plus minus 1 whole square, minus 1 minus 0 whole square plus 1 into half, which is 1. Once you have this information, this is true for all j, it is immediate that exponential m of k I plus 1 minus m of k I is 0, and the variance of m of k I plus 1 minus m of k I is equal to, I leave it to you to calculate this stuff. Our second property about this random walk is to show that this is also a martingale. You see, martingale thing comes up. So, symmetric random walk is a discrete martingale. So, you can easily prove that it is a martingale. So, you take any k strictly less than L and look at the expectation of ML conditioned on the filtration, the sigma algebra Fk, which is a part of the filtration. Okay. So, you can write this as ML minus Mk plus Mk so this can be summed up just like expectation can be summed, conditional expectation, this random variable can be decomposed into two parts, which you can actually prove, which will be a part of your exercise, but we are just using this fact here. So, maybe I should rub the board a bit. Now, let us look at the first part. Since L is strictly bigger than k, this increment ML minus Mk is independent of Fk. Fk does not have information of anything which is beyond the time k. So, here by one of our rules for conditional expectation, this is nothing but ML minus Mk, and here at time k everything about Mk is known. So, Fk contains all information about Mk. So, the first law was taking out what is known. I can write this Mk as Mk dot 1, where 1 is the constant random variable 1. So, whatever be the scenario, it will just give you the value 1. So, I can write this as Mk So, I write this as mk dot 1. So, it will, so I can take out what is known 1 dot fk. Of course, 1 is a constant random variable, it does not really depend on, is independent of fk. So, it will be E of 1, which is a constant, which will be just 1. So, because everything will be 1, so the sum of the probabilities will sum up to 1. So, the expectation will be just the number. So, this again is 0, which we already know, plus mk into 1, which is mk, and so this shows that ML is a this symmetric random walk, this thing forms a discrete martingale. Of course, Fk is mk has to be adapted to this filtration, that is the basic definition of martingale. There is another notion which crops up in the study of these sort of processes, is called the quadratic variation. So, you essentially look at path by path, you look at how much the random variable values are varying between one end of the path to other end of the path, that is between k1s and k2 say, how much it is varying, but do not take just the sum of those variations, they may just be 0. So, you just will not get any information, but take the square of the variation, it is like a mean square error type thing. So, we again we take here and introduce the notion of a quadratic variation. So, the quadratic variation is expressed in the following way. MMK is defined as summation j equal to 1 to k mj minus mj minus 1 whole square is equal to, and this if you look mj minus 1 whole square, this value is always 1. If you sum them up, what will be left here? Xj would be left here. The Xj, if you take the difference between Mj and Mj minus 1, you will have the value Xj left. Xj is either plus 1 or minus 1. So, the squaring will always give you 1. So, this expression of the square errors basically, or the square changes along every path of a given sample, I can do the take the changes, but it will whatever be your path independent of the path, it turns out to be k. If you do it up to the kth level, it turns out to be the k independent of the path that you have taken, which is very interesting. It does not happen for, suppose you want to compute the variance. So, MMK is actually variance of M of k. Think about it, how it is possible. But you see, to compute this, I really do not need to bother about the path, but to take variance of mk, we are essentially averaging over all the paths. So, this is a difference. Now, how do can I do something with this process? Can I increase the jiggling of this process a bit, this symmetric random walk a bit, and generate some sort of an approximation of a Brownian motion? Generate this sort of zigzagging that we had just seen in the beginning when I had drawn the picture of the stock price, that this sort of zigzagging. Can we generate this sort of zigzagging? This sort of zigzagging can be generated by using the symmetric random walk, and that leads to what is called a scaled symmetric random walk. We will not go too much of details into it, because that might take you off track and you might feel a little bit of discomfort for those who are not so very comfortable with very complicated analysis. So, what we are going to now show by this scaled random walk is that what we are going to show by scaled random walk is that we can construct an nth level approximation for the Brownian motion. Let us construct an nth level approximation. So, if you are zigzagging by say +1 and -1, I might zigzag by 1 by 10th and -1 by 10th. So, I will decrease my zigzagging steps, but increases my time size, right. So, we construct the scaled symmetric random walk, which is the nth level approximation of a Brownian motion, nth level approximation of a Brownian motion. So, all these are stochastic processes. So, this is a discrete stochastic process from which I am trying to go to a continuous stochastic process. I define it like this. You see, if I do not have nt to be an integer, I cannot define this. So, here my t is a t, say t between t starts from 0 and say it is up to t, or even t goes to infinity. So, basically for me here this t is just greater than equal to 0. So, I am using the discrete thing, I am trying to construct a continuous stochastic process. But I have to be aware that if I really want to use it, so at the nth level approximation, this mnt has to be, this nt has to be integer if I want to actually compute this. Otherwise, m is a discrete thing, it is computed only at integer points, you cannot compute it at non-integer points. So, what happens if it is not computed at, if nt does not turn out to be an integer? So, basically what you are considering, for n very large at various time points nt would be an integer and you are actually computing it out of nt. So, if nt is not an integer, take the t for which nt is not an integer, then take some u and take some s which is nearest to t such that ns and nu these are integers, and then compute the value of w nu and w ns and then make an interpolation, linear interpolation to approximate the value of w and t. And that is how you can actually do, you can generate it in a machine by taking a sample. Say you can take a sample of say, you can do the coin tossing 400 times with 1 by 10th, you can toss a coin 400 times with probability of half of going, you go 1 by 10th if it is h and you go -1 by 10th if it is tail. So, you decrease your movement. So, you actually increase the zigzag by decreasing the movement, and at every time you have to observe that your nt has to be an integer. Once you do that, you will find all the properties that you had of for here is in here, provided that this n into t is an integer. So, you first do it only for n into t is an integer, whatever is left you do the interpolation and you will see you will start getting a zigzagging curve, much zigzag than the symmetric random walk itself. Actually, it can be shown that as n tends to infinity, this wnt converges, this random variable converges almost surely not almost surely, I am making a mistake, converges in distribution rather, or converges in distribution. Okay, these are terms which I have not mentioned, just forget them for a while. Converges in some sense wnt as n becomes infinity, this stochastic processes gets changed into the what is called a Brownian motion. So, this is what we are going to talk about in the next class. So, tomorrow we are going to study the properties of Brownian motion for the next 2 classes. So, tomorrow's class would be the last for the second week of the course. In the third week we start continuing our discussion on Brownian motion and then go to understand stochastic integrals or Ito integrals and doing Ito calculus, which is the foundation of any financial mathematics that you do. Thank you very much.